Aloha, Rich Alverson here. This is its388al. And in this video, I'm going to try to get you through assignment 2, where we are enhancing our Mips simulator. So let me share my screen. Okay, here's the assignment. And basically, we're supposed to take the simulator that we did, that we made in assignment 1, which was just, translating the C version into the Python version. You didn't really have to know how the simulator worked. You just had to be clever enough to recognize the difference in the instruction sets and so on, or the the syntax and so on. So we're gonna add a jump instruction, branch if equal instruction, and then we're going to implement the offset parts of the two the load word and the store word instructions. So what does that mean? Well, first of all, let's start by running the let's start by executing the old program. Okay, so here's my command prompt, and I'm running and I've installed Python on my machine here, and simulator 1 is this one here. Okay, so and what I've done is I'm using a different editor this time. I think last time many of you thought that Edit Plus was the right editor to use for this, and actually it's not. The Edit Plus is not the right editor. I use Edit Plus because I started using it like 20 years ago or whatever, and I got bought a license way back then, and the license keeps on working. So anyway, I feel comfortable with it. But if you were to start a new editor today, I would either dive in and use Visual Studio Code, which is a Microsoft product, and there you have this development environment, and you run Python right in that environment, and it's the development environment that's used by lots and lots of software engineers, using lots and lots of different kinds of languages. But Python is the trouble with something like Visual Studio Code is we spend a lot of time learning the IDE. That's why we moved away from Visual Studio back in when we used to teach C#, but we've gone quite the opposite in quite the opposite direction, where any old text editor will do, and we just run our code from the command line, kind of like back in the old days before there was even Windows. But anyway, so this is the first simulator, and first let me run it. I'm at the I'm in the directory with the command prompt. If we do a dir, we see a bunch of my stuff, and I'm running this this one here, Mips 1 simulator py. That's the latest and greatest of my Mips 1 simulator, and I'm just going to run that to get to the Python 3. I have Python 2 and Python 3 in here, so I distinguish the two by typing Python 3 and then MIPS 1, and I only have to type enough until it knows the rest of it, till the rest is obvious, and there it is. So let me run this, okay, and we see I've modified the output a little bit. Okay, it does basically the same thing. It executes 4 instructions. It executes this ADDI instruction, and then it executes this load word instruction. Then it executes this add register to register instruction, and then it executes the store word instruction. That's all it does. And each time it executes an instruction, it prints out the contents, the status of the register file, T0 through up to T6 and so on. And it also prints out all of the contents of the memory locations that are not 0. When this thing is initialized, it initializes everything at 0, which isn't always the case in processors, but in this case, in this one, it is. And so that's one way of telling. Now, you'll notice mine looks different. And the reason is because I have modified these outputs a little bit. I, instead of just printing out all of the entire register file from 0 to 15 or whatever, it's the register file actually goes up. There's actually 32 registers in a Mips simulator. We're just using a small subset of the registers, and we're just using a small subset of the instructions. And so what and we rename these registers. So what I've done is I've modified the register print and the memory print so it uses the names that we're familiar with when we are writing the programs. And so you can do this to yours also. I've changed the print to where I create a register map saying the word 0 is register 0, T0 is actually RF8, T1 is actually RF9, T2 is actually RF10, and so on. Map this all the way up. SP, which is the stack pointer, we'll get to that later, is actually register 29, and then the return address register, which is actually 31. So it displays that out. And then for printing, what I do is I print out the memory address in the way we are used to referencing them, where we reference them starting from memory 5,000. So I say that instead of what the original code said. I don't remember what let's see, do I have, well, never mind. All right, so I've made those changes, and you can do that too. Here's the memory, the map register names, which I have just here as a comment. RF0 is this, RF8, RF9, and all the way up to RF31. Okay, and then I made another list, which is simply a list of character strings, and basically the location in the list is what the register name is. So location 0, and then there's no we don't use register 1, we don't use register 2 or 3 or 4 or 5 or 6 or 7, but we do use register 8, and we call that T0. Register 9 we call T1, 10, 11, 12, 13, 14, and then we don't use 15 all the way up to 29. This is 29, this is 30, and this is 31. So this is so I can map the other way. And you'll see where that comes in. All right, so this, okay, and then the other thing I have to do is when we reset the processor, this sets all the registers equal to 0, and this sets all the memory equal to 0, and this sets all the instruction memory equal to 0. And the thing is in the original, this only went up to 16, because that's how the farther we went. We have to go all the way up to 32, because we're actually zeroing out these up here also. All right, so and this was the program that our original simulator executed. Now you might not gotten far enough to actually realize what was going on here, but what this does is it loads the value 5,000 into register T6, and so now T6 contains 5,000. And then what this does is it loads the contents of the memory location specified by T6, which is 5,000, loads the value that's in that memory location into T0. That's what this load word instruction does. And then the next instruction took whatever was in T0 and added it to T0. So in other words, it doubled it. And it stored that value into T1. That's what the third instruction did. And then the fourth instruction took the value that was in register T0 and stored that into the memory location specified by the register T6. So in other words, it stored it back here. Let's see, do I have a copy of that? Guess I don't have a copy of that program, but what I wanted to do is well, let's make a quick copy. I'm going to take this, copy it, make a new file here, paste it, and I want to get rid of all the reason I'm doing this is because I actually want to execute this on the simulator, so you can see what see how it executes on the simulator. So you test your program. Okay, so this is the program that our simulator executes. And let's go back to here. Let's go to I'm going to section 310 on section on Mips simulators. And this is just a regular simulator here. It shows all the registers. It's nice. This one, well, let's go ahead and run it on this one. I'm going to paste the program I just copied, and then I'm going to enter the simulation, and then I can step through it if I want to. There, it puts 5,000 into T6. Next, it grabs 0 shoots. Let me exit the simulation. I should put something here because that's what we're taking. I'm going to put a value 22 there because that's what our simulator does. So let's try this again. 5,000 into T6, then it goes and gets what's in 5,000 and stores that in T0. And now it's going to take T0 and add it to T0 and store it in T1. And then it's going to do the last thing is it's going to save it back out here. Right. Now, so what we want to do, the way I'm going to do this is we have a simulator that executes these instructions the way they are. And what I'm going to do is I'm just going to modify this program a really little bit, adding these things that we want to do. And then we will just get our simulator to be able to execute the program exactly the way this thing executes. Okay, so first of all, I'm going to copy this back out again. And I'm going to go down here to this one, because this one actually shows the assembly machine instructions. And so let me reset this to initial. And I'm going to paste that program that I just made right here. Now when we assemble it, these are the ones and zeros that were right here. These ones and zeros. Okay, these ones and zeros are these ones and zeros right here. Okay. And if we execute this program, and we can put 22 here, and we can enter the simulation, and we can step through it, and we can see that it does what it does, and it's done. Oh, and then it starts over again. Okay, so let's modify this program a little bit. The first thing I'm going to do is I'm going to make this be a loop, and I'm going to make it so I'm going to put an instruction up at the top here. Okay, I got exit the simulation. I'm going to put the instruction up at the top, and I'm going to I tell you what, first what I'm going to do is I'm going to show you this. I'm going to change the code. I'm going to change it so see, this thing has all the functions that we want. So I'm going to instead of storing the doubled value back in the same location, I'm going to store it in the next location. So I'm going to make this be a 4 because this is an offset of 4 from T6. So now when we assemble this and we run it, 44 gets stored into the next. So now it's 22 and 44 instead of the 44 being stored back into the 22. Okay, so that's one thing I'm going to do. The next thing I'm going to do is I'm going to put a loop here. I'm going to increment T6 by 4. So in other words, instead of it addressing 5,000 and 5,004, I'm going to increment it by 4 and have it be addressing 5,004 and 5,008. Okay, so to do that, I'm going to down here. Let me exit the simulation. Down here, I'm just going to put ADDI T store back into T6. T6 plus 4. And then, okay, so that's that. And then I want to jump back to here. Okay, so I'm going to call this label 1. Done. Okay, so that's fine. I can do that, or I can put it on the next line. Okay, so and that'll be just a jump instruction I'll use. Jump L1. So what's going to happen is we should see this. It's going to increment T6 by 4, and then it's going to go back up to the top, and it's going to load in the T6 that it's going to load in the word that it just wrote, and then add double it and store it, 4 ahead and so on. And so let's see this work. I'm going to assemble it. Oh, it's got to be T6. Okay, assemble it. Looks like that. And let's step through it. I'll enter the simulation. So now it takes the 22, doubles it, stores it there. Then it increments this to T6. Now it's 5004. And it goes and grabs 5004, doubles it, puts it there, stores it in 5008. Then this goes up to 5008 now, and it just keeps on going. And the trouble is, if we keep this running, it's going to run forever. That's what they call a tight loop. Okay, so this thing would just keep on running forever. Well, we don't want it to run forever. We want it to stop at some point, okay? That's like having a while loop and not having a way to exit the while loop, okay? That's what this is. Well, we don't want this. Let's pause this and exit the simulation. And let's modify our program just a little bit more here. And I'm going to add, up at the top, I'm going to say, I want to do this from location 5,000 to, let's say, 5,020. Okay, that'll be like 5 times or something. 5 times 4 is 20. How about like, well, 5,020 would be 5 times. So I'm going to use T5 for that. So I'm going to load into T5 my stopping point. Basically, it's my stopping point, and I have to do this. I have to use an add I instruction for that because they know you can just do it this way, so they don't give you any other kind of instruction to do it with. Anyway, so I'm going to say it's going to go from 5,000 to it's got to be a multiple of 4. So let's do 5,028. That's a multiple of 4. It's like 7 times 4 is 28. So this is going to be the stopping point. Now, where do we put the check for the stopping point? Well, I guess let's put the check, since it starts out at 0. Let's put the checking point where after we've incremented, if we want to branch, if we want to branch if T5 is equal to T6. T5 is equal to T6. And we want to branch out. We want to branch to the end. We want to quit. So we have to put an end tag here. This is end. Got to put a colon there. Okay, so this checks if T5 is equal to T6. In other words, T6 is going to be incremented until it reaches 5028. That's going to be a multiple of 4, so it'll reach that. And when that happens, it's not going to branch. It's going to branch out to here. Otherwise, if this isn't equal yet, then it's just going to do this next instruction, which means it's going to go back up here, which means it's going to continue on. So this is our initialization, and this is our loop. And right here, to get out of the loop, we actually jump over this instruction here, and to the end. Okay, so we can assemble this. And this is what our code looks like. And so if this works, let's enter the simulation and let's start stepping through. Right, okay. So let me just run this. And we see it, so this T6, when T6 equals T5, then it's going to stop. In the meantime, it's going to keep on grabbing the number, doubling it, and storing it into the next one, storing it into 4 bytes later, which is the next address. And it should stop at 7 because we know that 7 times 4 is 28. 1, 2, 3, 4, 5, 6, 7. Okay. Oh, anyway, one more, it's equal, and now it's done. Okay, so did I 1, 2, 3, 4, 5, 6, 7, 8. Okay, so 7. Okay, so that's an off by 1 error. If you want to fix that, I did. This is just a test program. Anyway, so this is the test program. And this is the machine code. This is the actual program, and we're going to modify our simulator so it executes this code here. Okay, this is turning out to be a pretty long video, I know, but let's get moving here. Okay, so this is our Mips 1 simulator. I'm going to save this as Mips. I have a lot of versions of this. So this will be the Mips 2C simulator. Okay, here's the Mips 2C simulator. And so I'm going to leave this. That's fine. I have to put our new program over here. So why don't I just, first of all, let me just grab this. So I have this documented, copy, put that over here. Let me make this more organized, put this here, put this here. And so I'm going to do, instead of that, I'm going to overwrite that. And let me put, this is I'm going to do, and this is the program. And I'm going to do just so I have this. This is all going to be indented the same though. Okay, so this is my new program, and you can actually make this look nicer. Let me tab this out, tab this out. Okay, so this is the program. And we need to make this part now. This is the machine code instruction, line by line instruction. Well, that's this here. So let's grab this. However, I'm going to grab this, copy, and let's put them over here. I'm going to go to here, and I'm going to paste this here. All right, so I got this code here, and I got to make it look like this. So I got to take out the spaces, and I got to put this in front of every one of them. Okay. Sure. Okay, so let's do that. Oh, by the way, if you're using Edit Plus, no, Notepad++ for the first time, you want to make sure to go into settings, preferences, and this is for the tabs. This is to make sure the tabs end up right. Instead of general, click on language, and then click on. Oh, I better make sure this is because you want. Because you don't want to run into the problem where sometimes you're using tabs and sometimes you're using spaces. Because then you'll get this error of because this is a Python program, and so you get indentation errors. Python, we have indentation errors. So I would suggest click there, and then we're done. And then it's gonna, this is a space. Okay, anyway. Okay, so first of all, I'm going to copy this and I'm going to do edit, replace. Well, okay, forget it. Select this, Control H, and this thing comes up. And I don't want to do that. I want to replace every space with a nothing. And I want to do the extended. No, I'll leave that right now. In selection. I only want to do it in the selection. Okay, otherwise I'll get all messed up. So let me just replace all. Boom. Now all the spaces are gone. And now I got to put something like for every new line, for every new line. So make sure I say extended, because you want to recognize those. For every new line, I want copy this. For every new line, I want new line followed by that. Okay. Just in the selected area. Okay, just in here. Maybe like just in here, let's say, or something. All right, so I'm gonna do a replace. There we go. And then I got to change these so the increment. So I got to do some fancy down back 1, down back 2, down back 3, down back 4, down back 5, down back 6, down back 7. Okay. I guess that's all I need to do for that. Oh, it looks like that. Okay, so this is actually this. Okay, and I'm not going to bother putting the thing over here. Oh, but the end, we got to have this thing. And so instead of ending at 4, I guess it's going to end at 8. Yes. Okay, then this is the program counter. And let's go down here. And the first thing, let's just do all these at once, down the line. I'm gonna okay, so this is where we locate different fields in the instruction word. This is the opcode. That's always this is the yes, the opcode is you take IR and you shift it right 26 spaces, and that's going to shift off. Well, it's going to shift it all the way up, so you only have 31 to 26 left, and that's the opcode. And then after that, you have the RS field, the RT field, and RD field. And here where we we AND it with this binary number, and what's left is only these 6 bits, and then it's shifted 21 spaces. And for this one, it's only these 5 bits anyway, and so on. So that's how you extract off all these fields. That's the code for that. So just so you understand that, what we need to add here is we need to add one for the jump instruction. The jump instruction looks at all the bottom bits. Okay. So jump instruction has to have this. Yeah. I don't believe I showed this to you, but if you look in section 3.9, yeah, I think I did show this to you. These are the instructions that we're messing with. Where we have the LW and the SW, but the offset is not recognized. Okay, and we're simply adding the ability to put an offset, and that's why we're able to store it in the one leg. And still referencing, still using T6. We're able to store in the following address. So we're making this work and this work. These are already implemented. and we're implementing the BEQ. Now this is a label. Okay, so this is smaller. There's all these fields here. There's a for BEQ, you can see that there's a bunch of things here, and what's left down here is really only 16 bits. This is a 16-bit label, but what it is it's a relative label, which means relative to the instruction itself. So if it's only four away, this number is only 4. Whereas with a jump instruction, this is an entire address. This is the entire, you know, 26-bit address. Okay, and so that's this. This means jump, whatever it is, and this means the address, the absolute address. So anyway, so that's why we need to add this. So I've added that, and then now let's start messing with the LW. Well, for the LW, we have to add. We have to take a look at the offset field, and the offset field is it's this field. Okay, it's the offset field. So and we incorporate the offset right after we grab the address from the register. Then we take a look at the offset field. And remember, this is a 2's complement number now. So it can be a negative number, and it's an offset. So in other words, if you're branching to a negative number, you're branching back up again. If you're branching to a positive number, then you're branching down. Okay. So to convert to the 2's complement number, you take whatever value is in there and you subtract 65,536 from it. And is that right? I guess that's right. So I thought it would be 32,768. Anyway, we'll test it. We'll see if it works. So that's the oh no, if it's greater than this, then it's okay. Anyway, so that's the modification. So LW, so we now recognize the offset. So now we've basically implemented this one. So it recognizes a constant value there instead of it always having to be 0. So now it doesn't always have to be 0. It can be an offset value. Okay, so that's for that one. We need to add, we just do exactly the same thing. After we get the base address, we can paste in if the lower 16 bits is greater than 768, then it's a negative number. Then we subtract this from that to get to the negative number. Otherwise, if it's smaller than 32,768, then it's a positive number. So this adds that offset to the address that we grabbed out of the reference. So in other words, in our context, this is good. This is T6. So we grab out this thing, which is called the address, out of T6. We add the offset to it. And then we go out to memory. We go out to data memory. Oh, okay, this is storing. So here we're storing to data memory. Here, up here, load, we would be loading from data memory. Right here. Yes, this goes and grabs out the value from data memory, which is this, and then this stores it into the register. That's what this does. Okay, so that takes care of load word and store word. Then we got a mess. Oh, then we have to add the jump instruction and the BEQ instruction. Okay, so let's start with adding the jump instruction. I'll just pop that in down here. by the way, you may notice these are the modifications that you have to make to print the register names. Let's see, I guess like these things here. Like that. See, this is the PM5000. Anyway, so you can look closely and replicate that. So yours might look a little different. By the way, this isn't a requirement for the assignment. The original way you had it was fine. I just did it this way to make it easier to understand. All right, so I'm just going to paste these in here and explain what they are. Let me copy this. So for the this is make sure this line up. Okay, so this is the jump instruction. So if the upper 6 bits are 0000010, then it's a jump instruction, and so it prints out this jump to the label, or jump to a label, and the label is going to be the entire rest of the word. So it's going to be the lower. This is the upper 6 bits, and this will be the lower 26 bits, which is an absolute memory address. Okay, it ends up being a 28-bit memory address because the lower 2 bits are 0 because it's every 4, because a instruction memory is every 4 memory locations. All right, so so this says what the opcode is. This identifies the label. It prints that out, and it's going to print this jump instruction, which is going to show that it, this value, which jumps directly to the label. So you'll see that when this executes, this multiplies the label by 4 because that takes care of the fact that it's every 4 bytes. All right, so that's the jump instruction. And the branch instruction is, I guess it's a little more, there's just a little bit more explanation going on, I guess. Copy this and paste it. Okay, the opcode is 000100. It's an opcode. It's a branch if equal. If this register, the contents of this register is equal to the contents of this register, then jump to this label. And this label is a relative label, not a. So we add this label to the program counter. For the jump, we actually. Okay, oh, let me just put it. Let me put space. For the jump, you see, we actually replace the program counter, the program address register. We replace it with the label ×4. So it just overwrites the whole thing. For a branch, it's a relative address, so it's relative to what the program counter currently is. So we add it. We add the label, or if it's a negative number, it'll end up being subtracting a value from the program counter. See, so this is nothing here. This was a mistake. So here we check to see it's the same thing applies, or no, the relative part applies. We have to see if it's a negative number. If it's a negative number, we subtract 65,536 from it, and so that's the negative number. And we take the instruction register and we take this value and we add 1 to it. That's because the program counter is actually one. It actually points to the next instruction, not the current instruction. It goes with how processors are designed. And and at what time does the program counter advanced. Anyway, so here it checks to see if this register is equal to this register, and if it is, add the computed label to it. And that's all it is. And then this is just a bunch of stuff to print everything out so you understand what's going on. And this is the final thing that prints out. So let's I guess let's see if this runs. Now we start out again, our simulator loads. What is it? Oh, here it just loads into location 5,000. This is location 5,000. It's convoluted way of getting to 5,000. It loads the value 22 into location 5,000. That's where this 22 always comes from. So let's just leave it at that. And this is the program that supposedly ran successfully before. I'm going to save this, and I'm going to go here, and I'm going to first clear out the screen so I don't get confused. And then I'm going to do Python 3 space MIPS, and this was 2C. Yes, 2C simulator. And well, so this shows the status after every execution. Let's start just real quickly here. This is the add. Start up by loading 5028 into T5. Remember, that's where we're going to stop. Then we load 5,000 into T6. And then we're going to, and this contains 22 because our simulator loaded that in. And then we're going to load whatever is in 5,000 into RT, or basically we're going to load whatever is 5,000 into T0. And then so now when we list out T0, we see that 22 is in T0. And then we're going to add T0 to T0 and store it in T1. T0, well, anyway, T0 plus T0 equals T1. And so now we see 44 is in T1. And then this one stores the word back out into, stores it into T1, stores T1 into 5004. 5004 is, it's the result of, well, anyway, that's what it should be. 5004. Where's T6? One of these is addressing T6. This is T6. T6. This is T1. And this is the offset, which is 4. 100 is offset 4. Anyway, so and then we add 4 to T6. T6 plus 4 and store that into T6. This. And then here's the BEQ instruction. BEQ is the opcode is this, and then it's register T5 is equal to register T6, and this is the label. Now the label is just 1, and you add 2 zeros, so it's 4. See, so if it ends up being true, it's going to add 4, 1 plus followed by 2 zeros. It's going to add the value 4 to the program counter, and that's basically jumping around the next instruction. The next instruction is this label, jump to label, and this thing jumps all the way to location 2, or would it add 2 zeros, so it ends up being the third memory location in the third instruction in the instruction memory. Anyway, so now now it continues on because it's looping. See, it's looping, and then each time it's adding more. It's adding more here. Keeps on adding more in the very end. It's got, you know, the zero, the okay, 1, 2, 3, 4, 5, 6, 7, 8. Okay, so 2816 is the last one. Just like this one is. 2816 is the last one. So anyway, I think that's enough. That should um help you do assignment 2. Thanks for watching.